So we're getting ready to open Magic, and I'm going to bring up the design manager over here, a project manager, and my project is called Layout 1, and I'm going to edit it. So this is really, expand this window all the way so we can have a full view. Hitting F gives me a full view of my two cells. It's a very simple example that has a couple inverters shown over here, and this is really just to give an overview of Magic. Few different areas on the workspace. At the bottom you have a feedback area that shows you feedback from various commands. Top is several menus regarding file editing, editing individual cells, hierarchy control, expanding cells, window control, including setting grids, zooming in and out, different things on layers, DRCs, options, and devices that you can include, very similar to P-cells in other programs. There is an interactive DRC which currently is checked. You can click on it to turn it on or off. The overhead is fairly small, lots of spacing rules and minimum width being checked on the fly for you. So if you're not exactly sure what a design rule is, you can actually see interactively what happens. The cell we have is currently, it's called Layout 1, and that's the one we're in edit mode right now. There are 4 different tools in Magic. One of them is Box. It's probably the one you'll use the most often, and I will go over how its operation just shortly. Technology right now is the eFabless XH035A, which is the base process for XFAB 0.35 micron process. Right side, you can see different layers that are available for painting. The rest is mostly just information layer you cannot edit in this version of Magic. So this example over here has a couple cells in here. It's fairly straightforward. Let me just do a few things first to get started. First, setting a grid is usually a good idea, and I'm going to use a 1 micron grid just to get started, which starts showing up so you can see these are fairly small cells. This layout has 2 identical cells that were placed. The type is called INV1. The instance is called INV1_0, INV1_1, 2 separate cells in here. So to select a cell, there's a couple ways you can do that. Either you highlight, basically hitting the S key for select over the area of interest will select the area over your cursor if it's a cell, which I've just done over here. And using the // you can expand and unexpand that particular cell. So if I hit / repetitively, it'll toggle between expand and unexpand, which you can also do from over here using expand and unexpand, and I'm using the toggle in this particular case to switch view. I can select again individual transistor. In this case, there's a PMOS device over here, and over here, after selecting and using the // I can actually see what the entire cell is made of. So there's a PMOS device over here, there's an NMOS device. The Magic differs from standard layout GDS2 based layout tool in that a lot of the things that you're seeing are actually abstracted view, which makes things fairly easy to look at. So a couple basics first. This is the box tool, which means you have to draw a box to do anything useful, generally speaking. So the box is, generally speaking, left button click will set the bottom left origin of the box. Right click will set the top right part of the box. So you can see here my box is between here and here. It's actually a little hard to see. I'm going to hit SZ to zoom on the box. It's a little hard to see here. I remove the grid. You can see the box area over here. I turn the grid back on. Little G turns the grid back on and off. Kind of easy. You can also toggle it from the window by turning the grid on or off very easily. So a capital Z will zoom out. So it's an easy way to get around. You can actually do a box selection over here. Hit little Z, which will zoom precisely on the box area and zoom you in. If you want to zoom back out, you can zoom out. Or F actually will give you a full view of the entire cell that you're editing. So I'm going to hit Z again just to focus on that NMOS. So as I mentioned earlier, unlike standard layout tools, a lot of things you see here are abstracted. And let's start with what we're looking at. These are two NMOS devices. And I know they're NMOS for at least one reason, which is the diffusion area is green. Green is typically an N diffusion, and poly is typically represented in red, which is what you're seeing over here. And I know that a poly over a diffusion typically is an NMOS transistor. So this area over here is an NMOS transistor. There's a second one over here, very easy to see. The big contacts over here, represented by essentially this big X, and the box over here is actually more than just a contact. It's a combination of N diffusion, contact, and metal. The cut opening is actually not exactly what you see here. It's going to be on the inside. They're going to be inside. There's going to be multiple contacts at GDS time, but it's a lot easier to see this way. And this could be a drain, source, drain, or the other way around, source, drain, source, depending on how you connect things in here. But you can easily see you have two NMOS devices, a couple of contacts. The cell itself is drawn with a fully guarded device. You have a P+ ring around this device and a couple contact to the guard ring around. It's good practice to do that. And if I go back, let me zoom out a little bit and now zoom on the P device. The P device is constructed very similar construction. And it's a P device because it has a P diffusion, which is typically a brown shaded area with poly on top of it. Again, you have drain, source, drain contacts of two different devices. The drain area is actually shared. And the device again is fully guarded with an N+ diffusion area guard ring all the way around. You can see the NOL, which is this slanted shading over here, is the NOL area in which the device is contained. Let me zoom out again a little bit. So one of the nice features of Magic is actually very easy to go and trace things. In this particular example, the metal one is actually colored in blue, and as a matter of fact, you find the same thing over here. These are the various areas you have. So this is metal 1. Metal 2 would be this pink. Metal 3 is this other stitched pattern over here. Earlier I mentioned if you want to select something and hit S. Now if the cell is unexpanded like this inverter over here, it will actually select the entire cell. If the cell expanded, if you hover your cursor around it, over it, you will actually start selecting the piece of material that's directly underneath. And if I zoom in here just a little bit, you can see the first time I hit S, I select the very first piece of metal. If I select the second one, it's going to select all the metal 1 connected to it. If I select this third time without moving my cursor, it's actually going to select anything that's physically connected, or electrically connected to this in signal. And you can see that both of my devices here, both the PMOS and the NMOS, have their gates connected to the input, which is not very surprising since this is an inverter. I can do the same thing on the out over here, and I can select over here, and you can see that now it's selecting the output drains of the PMOS and the NMOS. Very convenient. Let me now go over NV1, select, again, use S1, which will select this guy, and I'm going to use the toggle expand, the / to select the second inverter. And now if I go back again on the out node of the very first one into the in node of the second one, you can see exactly how things connect, and you can see that the drain of the first inverters, the drains of the first inverter, connect to the gates of the second inverter. And then again, I can repeat this over here, using S repetitively, and you can see the output gate. So it's very easy to trace signals in Magic. It's one of the advantages. I can actually do that also on the ground side. Let me do this on the ground nodes over here. So actually, the first time I hit S, I end up selecting the substrate area, which is not what I want. So I'm going to hit S again. It looks like I'm selecting part of the guard ring over here. One more time. I have the whole guard ring, but the guard ring being connected to ground, I actually end up selecting ground. So if you zoom into this area, you can see that ground consists of the metal 1, which is a big thick trace over here, but it connects to the guard ring and the substrate, obviously. But it also connects to the sources of this, the first device, and the sources of the second device. in a very symmetrical manner, the VDD over here will connect to, oops, let me hit this repetitively, there we go. So the VDD node over here connects to the sources of the PMOS. It connects also to the guard ring via those connectors over here, but and also highlights the NOL, which is all around over here, of the device. So it's an easy way to check for connectivity in here. It's really built in. One of the advantages as well is that regardless of the technology you end up using, the devices tend to look the same. So these are PMOS, and the PMOS will look the same almost regardless of the technology, which is really nice. The NMOS will usually look the same regardless of the technology. If you want to measure the device, actually, there's a very easy way to do that. You go and put your cursor above the area of interest. I'm going to hit S. Now, first time it's not what I want. I want to get that gate. So I'm going to hit S repetitively until the gates get selected. And here's the gate over here. And I can do a, let's see, wrong place, measure box in the window menu. And this will tell me exactly what is the size of this box over here. And it's telling me this is 10 micron by 0.5 micron. So this is not a minimum size device. It could have been 0.35 micron. It's a half micron width, 10 micron device. There's two in parallel. It's a 20 by 0.5 device. Very easy to go and measure things. Let's see. Couple more things. So I'm going to, so if I want to select, when things are unexpanded, and you actually want to select a cell as opposed to material, you can use Control-I, and this will if you hit it repetitively without moving the cursor, the first time it's going to select the lowest cell that you have available. Here it's the PMOS. If I hit it second time, it's going to select the inverter, which is next level up, or in the last time, I'm going to get layout 1, which is my top level cells. And if I start again, it's just going to circle through. So I can select INV1, hit the /, and I'm going to unexpand that particular cell. I'm going to do this again, Control-I, first time, second time I get INV1, /, and I'm back to where I was originally. And if I hit F, you get a full view. I go back to my full view over here. Very straightforward. If I wanted to add another inverter, there's a couple ways of doing that. Easiest is to select the first inverter, and then what I'm going to do is I'm going to hit C for copy. And the way Magic copies is it'll take the lower left corner of the area I've selected, and it's going to copy that lower left corner to wherever my cursor is. So if I put my cursor here and I hit C for copy, it's creating a third copy of INV1, 1, 2, and 3. Notice this area over here that's highlighted in white. It's actually DRC errors that had just happened. And my DRC count here is telling me there are 2 errors right now. So I'm going to expand that cell, /. I'm going to select this one using S, /. And if I zoom in over here, I can hit the Y letter. And it's telling me my NOL spacing is too close. It should be at least 3 micron. And you can see here, I'm on the 1 micron grid. I'm definitely less than 1 micron. As a matter of fact, if I were to change the grid and go to maybe 0.1 micron, my grid right now, and I'm going to hit B for, to the box over here, and I ask on the window for measure box. This box is only 0.7 micron wide, clearly not enough. So I have 2 solutions at this point. I'm going to zoom out a little bit, and if I select this cell over here, INV1, so I can move it with the arrow, and it's going to move on the grid. I can start moving it until I get no more errors. And oops, actually, okay, here I still have 1, and here I have no more errors, which means I must be exactly 3 micron away. Measure box. I'm exactly 3 micron away from the other one. Now, obviously, it's not a very efficient layout. And if you look at this very first device over here, you can see that we had the guard ring contacts overlap exactly from cell to cell. So I'm going to select this cell over here again, and I'm going to move it back. I'm going to move it back until I get an exact overlap of my contacts, and you can see the DRC errors now just went away completely. It's a fairly packed layout. And from the position of the output and the input, I'm connecting these guys next to each other. Fairly straightforward way to do things. Very easy to follow layout. So this is really just an introduction. And in the next tutorial, I will be explaining a little bit how to connect wires and do slightly more complicated things. Thank you.